In this video, we're going to draw some Lewis structures that have some exceptions to them. The two main exceptions you'll see in Lewis structures are what's called the incomplete octet and the expanded octet. There's some video links in the handout that you can watch to get some more details on each of these, but we'll briefly explain what these are here and then do some examples. So the incomplete octet is the case where you can have less than 8 valence electrons and still be satisfied. And you've actually seen that example before when we did the example of CH4, like this. Carbon had its complete valence shell, 8 electrons, but hydrogen only had 2 electrons in the bond there. It didn't have anything else around it, and it doesn't need anything else around it because hydrogen only has that 1s orbital or sublevel to fill up, and that's it. So it's happy just having 2 electrons in there. So that's the first example we saw of the incomplete octet with hydrogen because it only has 1 valence shell. But there are some elements that have more than one shell. So their valence shell is not their first one, like hydrogen. And they are still happy with having less than 8 electrons in their valence shell. And those two that you need to memorize are beryllium and boron. Beryllium is happy with 4 electrons in its valence shell, and boron is happy with 6 electrons in its valence shell. So let's go take a look at an example. Here we have BH3. And so when we have BH3, we'll follow the same rules that you'd normally do for your Lewis structures. You try to calculate the number of valence electrons in boron and then the number of valence electrons in hydrogen. And so if we look at boron, boron's over here in group 13. It has 3 valence electrons to contribute to this Lewis structure. So boron, 3 valence electrons, and then hydrogen, don't forget there's 3 of them, so 1 times 3, 3 valence electrons as well. So it's a total of 6 valence electrons to place. And so we're going to go ahead and do that. We're going to put our boron in the center because we don't have a lot of it. And we'll put our hydrogens kind of all the way around like this. And we're going to connect them with single bonds. And when we do that, we place 3 single bonds. And so that's 6 electrons gone, 0. 0 left to place. Our hydrogens are all happy because they're 2 each. But our boron, you'll notice, only has 6 valence electrons from the 3 bonds there. And typically when you run out and you don't have enough for everybody to be satisfied, you would go to the peripherals and ask to make some double bonds. But in this case, you can't do that. You'll notice the hydrogen doesn't have any lone pairs to donate to share to make multiple bonds. So that's okay. This molecule can still form as BH3 just like this, and it's happy and stable that way. And boron would still follow this rule even if you had peripheral atoms with lone pairs to donate. So for example, let's say you want to draw BCl3. So B has 3 valence electrons. Cl has 7 times 3. That's 21. So that's a total of 24 valence electrons. And so we're going to draw our boron in the middle, and we'll put our carbons, our chlorines, just evenly distributed around here, and we'll connect them by single bonds like this. And so that's 6 electrons placed. That's 18 valence electrons left over. And so we're going to go and place them around our peripheral atoms first until they're happy. And we'll have 1, 2, 3, 4, 5, 6. That's happy. 1, 2, 3, 4, 5, 6. That's happy because of the single bond there. And then 1, 2, 3, 4, 5, 6. We've placed 18 electrons at this point. We ran out of electrons to place. And so you'll notice boron is not happy. It has 6 valence electrons because there's 3 single bonds. And you would think, well, let me go to chlorine and do this. Let me go to chlorine and make a double bond with boron and get something like this. And then you'd say, well, boron's happy now, so this is a better structure. This is actually not what happens. Based on experimental evidence, we see that boron actually still would prefer, or the preferred structure is still the boron Cl3 there, BCl3, with the single bonds only. So even when you do have the ability to make double bonds or triple bonds or whatever be the case, when something's connected to boron as a central atom, you leave it as an incomplete octet. So they want to be incomplete octets when they can be. So don't make double bonds there because that's not the best structure for boron. And the same thing would apply to beryllium. So suppose we had a molecule of beryllium. Here's another example here. So we have a beryllium, this BH2 molecule here. We're going to count the number of valence electrons. Beryllium is in group 2, so 2 valence electrons for beryllium. And then hydrogen, well, there's 1 times 2 hydrogens. That's 2 valence electrons there. And what you'll notice is that if you do 2 plus 2, that's 4 valence electrons a place. And so we'll go ahead and put beryllium in the center. And we're going to connect our hydrogens with the single bonds. And when we do that, you'll notice that we've already placed 4 electrons. There's 0 left. Beryllium is not happy, you would think, because there's only 4 valence electrons there. But it's actually stable like that. That structure works for it. The same thing if you had, and notice that, typically it would say, well, I'd go and borrow electrons from the peripheral to make multiple bonds. You can't do that with hydrogen. But even if you could do that with the molecules that are, so let's say you had BCl2. So for Be, you have 2 valence electrons. For Cl, you have 7 times 2, that's 14. Oops, times 2, that's 14 valence electrons. That's a total of 16 valence electrons a place. Well, now what we're going to do is we're going to go ahead and place our chlorines with their single bonds here. And that means we've already placed 4 electrons, so we have 12 left to place. We'll place them around the peripheral atoms until they're happy, just like this. And now we've run out of electrons, and so there's 0. And you might say, well, I can make some double bonds. So I can go ahead and do this and borrow some electrons from the chlorines there and make a double bond here, and then do the same thing here, almost like carbon dioxide. So you'd think that would be the best approach to do. But with beryllium in there, because it has the incomplete octet as its preferred structure, we wouldn't do this. You would leave it as just 4 electrons in the valence shell, and that's it. So boron is good with the 6 electrons in the valence. Boron is good with 6 electrons in the valence shell. Beryllium is good with 4 electrons in the valence shell. So 4 keeps it happy. Boron 6 keeps it happy. Don't go try to play with it and make double bonds and triple bonds there. As long as it has the beryllium 4 and boron 6 and hydrogen 2, you've met their happiness conditions and they're good. So that's one of the main exceptions you'll often see in Lewis structures. Another exception you might see is something called an expanded octet. So an expanded octet is what the term says. It's more than 8. It's expanded. It's beyond 8. So this usually is going to happen with elements that are in the periodic table from period 3 and beyond. If they're in period 2, if elements are in period 2, they cannot have an expanded octet. So let me just erase some of the work here and we'll do some examples of expanded octet. So expanded octets are elements that are period 3 and beyond in our periodic table. So if we go here, when you get to period 3, elements like phosphorus, sulfur, they can have expanded octets, but anything below that can't have expanded octets. So, carbon will never have more than 8, nitrogen never have more than 8, oxygen will never have more than 8. So anything in period 2 and below cannot, but period 3 and above, they can have expanded octets. So period 3 and beyond. And the reason for this, and I put a video link that you'll see in the main handout that you can go watch for more details. But the main reason for this is because you have access to d orbitals. And those d orbitals are not so high energy that you can't access them for bonding. You can actually access them for bonding once you get into that 3rd period. So if you have access to d orbitals in the 3rd period, you can use those for bonding purposes. So for period 3 and beyond, you can have expanded octets. There's nothing wrong with that. We'll do a couple examples here. So let's do the example of SH6. So here I have SH6. And in SH6, you're going to see that sulfur has 6 valence electrons. And then for hydrogen, there's 1 valence electron, but there's 6 of them. So that's 6 valence electrons there to place. And that's going to give us 6 plus 6, 12 electrons a place, 12 valence electrons. So what we're going to do is we're going to draw our central atom, which is sulfur. There's only one of it. And then place our hydrogens around sulfur. So we always start off with the same basic steps. This is 6 hydrogens, 1, 2, 3, 4, 5, 6. We're going to connect them all to sulfur using single bonds. And once we've done that, since there's 6 single bonds, we've placed 12 electrons, there's 0 left to place. All the hydrogens are happy because they have 2 each. But notice if you count sulfur, sulfur has 2 per line. So 2, 4, 6, 8, 10, 12. Sulfur here has 12 valence electrons. And you might think that that's wrong because you should only have 8 as an octet, but because sulfur, let's go back and look at our periodic table here, is in period 3, it will have access to bonding electrons in a d orbital that's not too much higher in energy than the other orbitals there. So that's okay. This is an expanded octet and it works out just fine. So if you see situations like that, it's not breaking a rule because we're in period 3 or beyond, we're allowed to do that. Another example we can do is, let's try this one here. We'll do Xenon Difluoride. And we're going to try to see which exception it is. It could either be the incomplete or the expanded. So let's take a look. So we're going to choose xenon here as being our central atom, and then fluorine will be the peripheral atom since there's more of them. They're also more electronegative. But let's go count. So xenon's in group 18. So xenon would have 8 valence electrons. Fluorine is going to have 7 times 2, 14 valence electrons. And so that's going to give us 22 valence electrons to place. So let's go ahead and start placing them. We have xenon, and we're going to place fluorine off to the side there. And we're going to connect them with single bonds. And when we do that, we've placed 4 electrons already. We have 18 left to place. So let's go put them around our peripheral atoms until they're happy. So right now, I've placed a total of 6 around the first fluorine. That's 12 left to place, and that first fluorine's happy. Around the next fluorine, that fluorine there is now happy, and that means there's 6 electrons left to place. And so I still have electrons. My fluorines are happy. They typically won't have expanded octets. When I say expanded, it's typically going to apply to that central atom, not the peripheral one. So you want to focus on the central atom when it comes to expanded, and same thing with incomplete, with the exception of hydrogen, of course. That's going to be on the peripheries for the most part. So we're going to place our 6 electrons around xenon. So we'll have a pair here, a pair here, and then a pair here. I don't want to put all the pairs too close together because they're electrons, they repel each other. So I try to evenly distribute them to minimize that repulsion, which you might remember from grade 11 if you learned it, Vesper theory a bit. But now we've placed all 6 electrons there, and so we don't have any more left to place. And so it looks kind of odd because if you count the electrons on xenon, you have 2 from this bond, 2 from this bond, 2 here, 2 here, 2 here. So that's 2, 4, 6, 8, 10. That's 10 valence electrons surrounding xenon. So what exception is this? It's more than 8. This is an example of an expanded octet. So again, if you're in period 3 and beyond, you can have expanded octets. Don't give expanded octets to anything below period 3. So if you have carbon and you do 1, 2, 3, 4, so let's say you have this going on here, and then somehow you have another bond over here with something else here. If you have these 5 bonds, this is 8 there plus this, that's 10. This would be wrong. So the ones in period 2 and below, they just don't have access. That d orbital is too high up in energy for it to be accessible for bonding. So you cannot do that if it's below period 3. But period 3, central atoms can often experience the expanded octet. And don't forget about the incomplete octets when you're drawing. Do not try to give them multiple bonds to think you're making them happy. They're happy the way they are. So in the next video, we're going to do some examples where we'll draw some Lewis structures for polyatomic ions, and we'll also see the concept of resonance structures.